Okay, now we will discuss about the parameter used in open channel flow analysis. Okay, in open channel flow, as you know, the cross-sectional of open channel flow is not always circular. Sometimes it can be rectangular, sometimes it can be trapezium, sometimes it can be triangular, and sometimes it can be unpredictable shape. For example, if you do analysis for river, so mean the cross-sectional river is unpredictable because it has a natural shape and so on and so forth. So means that in open channel flow, you cannot use diameter because sometimes if your open channel flow is circular, even you have a circular pipe like this, and then the water is for example 2/3 of the level here, you still cannot use the diameter because the diameter is actually the distance from this surface to this surface, means from this edge to this edge. This is diameter, but the water is actually from this surface to this surface, so means that the usage of diameter is improper. Okay, you maybe say that, okay, from here to here is diameter, but from here to here it's not the diameter of the pipe. So means the usage of diameter is incorrect. Okay, to calculate that one, okay, we propose one term, very important. This is your first time to hear this, so we need to understand, we need to know the hydraulic radius. So this is the first equation that we learned in this topic. We call it as the hydraulic radius. So the symbol is RH. So the hydraulic radius means, okay, we try to give the imaginary radius of non-circular shape. So this is the basic idea of hydraulic radius. Okay, so what is the equation of hydraulic radius? Okay, the equation is RH is equal to A over WP, which is A here is the flow cross-sectional area. So you need to remember this. And the WP here is the wetted parameter. Okay, I will show you the example after this. So, but please remember these two equations. So, and then the diameter, the hydraulic diameter is equal to 4 hydraulic radius. Okay, it is not same with the common diameter, which is equal to 2R. So for hydraulic diameter, it is equal to 4R. So you need to remember this equation. Okay, so and then the meaning of this equation is RH is hydraulic radius, DH mean hydraulic diameter, and A is flow cross-sectional area, and then the WP is wetted parameter. You need to remember the word flow here. Why? Because this is the explanation of the equation. Okay, let's say we have a circular shape of pipe here, but the water level is half of it like this. So means that here the atmospheric pressure acts on the surface. So means that this flow is now can be classified as open channel flow. So and then because the water is half this section, we cannot use diameter or radius only because it's not reflect the real flow situation. But we need to calculate the hydraulic radius. So the equation for hydraulic radius, we have RH is equal to A over WP. Okay. So and then A here means the flow cross-sectional. So what is the meaning of flow cross-sectional? You need to see the water flow. So the water is here, okay, and then you need to know the area of the water cross-sectional. So means you need to calculate only this area. That's why we write as flow cross-sectional. You only calculate the cross-sectional created by the fluid, not the cross-sectional of the pipe or cross-sectional of the conduit. Okay, you need to really understand that. Boleh faham So maksud A ialah cross-sectional, tetapi awak perlu ambil cross-sectional air yang berada di dalam saliran tersebut. Maksudnya jika air tersebut separuh seperti ini, awak hanya perlu mengambil nilai ini sahaja. Kita kena mengira nilai luas. So in this situation, we found that the A is equal to pi d square over 8. We know that the total area for the circular is pi d square over 4, and then we divide it into half, so we will get pi d square over 8. Okay, I hope you could understand this one. And then the WP here means the wetted parameter. So wetted parameter kita terjemahkan sebagai parameter kawasan yang dibasahi oleh air. Means the parameter wetted by the fluid. So it is wetted parameter. So in this case, the wetted parameter is actually area where the water stick or the water touch the structure. So means that this is only the wetted parameter. Okay, so means the wetted parameter is pi d over 2 because we know that pi r square or pi d is the parameter, the total parameter for a circular shape, and then we divide into 2, so we have pi d over 2. Okay, this area it cannot be calculated as wetted parameter because this area we have liquid and gas interaction. Liquid and gas interaction will not give no slip condition, as we know about the maximum velocity contour just now. We found that there are no slip condition here, so means that the water is still moving on the surface. That's why we cannot count this area as wetted parameter. So if you have this one, so you have a pi d square over 8 as the flow cross-sectional area, and the wetted parameter will become pi d over 2. Okay, this is for the circular shape. And then I hope you could understand this one. So the flow cross-sectional area is W times D because the water level is only D. And then the wetted parameter is D plus W and then plus D. So that's why we have W plus 2D. So, and then this is the trapezoidal channel, and this is the irregular shape. For the irregular shape, okay, you need to do by any method. You need to calculate what is the area of the irregular shape, and then this is the wetted parameter, and then you need to calculate the area here. Then you will get the hydraulic radius. Okay, this might be the quite challenges work in open channel. Okay, but in our syllabus, we always use circular, rectangular like this, and also the trapezium. The trapezium like this. Okay, for the trapezium like this, so I hope you could calculate by any methods, by any means. Means if you want to calculate the wetted parameter, you need to know the length here, plus with this length, and plus with this length. And then you need to calculate the area of the water here, the cross-sectional area of water here. Then you could calculate the hydraulic radius by using this equation. Okay, so I hope you could understand about the hydraulic radius. Then we go for the second equation, which is the Reynolds number for open channel flow. So I think you are very familiar with the Reynolds number because we are using Reynolds number to determine whether the flow is laminar or turbulent in flow in pipe. So I think you already know the equation here. So Reynolds number is equal to rho Vd over mu or Vd over nu. So mu here is the dynamic viscosity and nu here is the kinematic viscosity. I hope you remember this equation. Okay, from our previous flow in pipe, okay, we found that if the Reynolds number is less than 2000, so we could categorize it as laminar flow. But if the Reynolds number is more than 4,000, so we could say that the flow is turbulent flow. So what happened between 2,000 and 4,000? So we call it as transition region. Okay, so we learned this in Fluid Mechanics 1. Okay, so but in open channel, we cannot use this equation because, as I said, we don't have diameter. If our conduit is rectangular or triangular, so we don't have diameter for that shape. Okay, so we change the equation here, okay, by the idea of similarity or dimensional analysis. Okay, I'm not to explain that. Okay, to simplify that, okay, we change the value of D here with the hydraulic radius. So now the equation for Reynolds number for open channel will become rho VR over mu or VR over nu. So which is the mu here is the dynamic viscosity, nu here, okay, actually this is the same symbol. Okay, I make mistake here. So the nu here is the kinematic viscosity. So the only changes is the diameter here is changed with the hydraulic radius. And then the limitation of the Reynolds number is also changed. In open channel, if the Reynolds number is less than 500, so we could assume that the flow is laminar. And if the Reynolds number is more than 2,000, so we assume it is fully turbulent. So what happened between 500 to 2,000? So it is a transition. So transition region means they are mixing from laminar to turbulent. So as you know that, for example, this is laminar and this is turbulent. So and then the transition means they are some certain percentage of laminar and turbulent. So for example, if the Reynolds number is 1,500 around this area, so maybe the laminar is around 30%, but the turbulent is 70%. If the Reynolds number is around 700, maybe the laminar is 70%, the turbulent is 30%. Means that the changes occur in transition region. Okay, so please remember this one, and please remember the limit here, because the limit is different from the flow in pipe. So and then I would like to introduce you another dimensionless number that very important in open channel flow. Okay, in flow in pipe, we always use Reynolds number because we have diameter to calculate. But for open channel flow, we don't have diameter. That's why the Reynolds number is actually only used to determine whether it is laminar or turbulent. So I would like to propose here the Froude number. If you still remember, in your Fluid Mechanics 1, in dimensionless analysis, actually, a part of your notes is about the calculation or how to get Froude number from the dimensionless analysis. Okay, so I skip that. So because we already learned that in Fluid Mechanics 1. Okay, the Froude number, the symbol is Fr, and it is the flow velocity divided by surface wave speed. So and then the equation will become V over square root GYH, which is the V is the velocity, the G is the gravity, and the YH is the hydraulic depth. Okay, so and then how to calculate the hydraulic depth? So it is the A over T, which is the A is actually the flow cross-sectional area, as I explained previously in hydraulic radius. And the T is the top width of the channel. So for example, if we have a triangular shape like this, and the water only at this level, Okay, first you need to calculate what is the area of the flow cross-sectional area, which is this flow, this area. And then you need to calculate the top width of the channel. You need to calculate the top width of the channel. So this is the top width, the T of the channel, and this is the A. Okay, then if you divide A over T, you will get the hydraulic depth of YH here, and then you could substitute into the equation, you will get the Froude number. Okay, so why Froude number is more important compared to Bernoulli equation, compared to Reynolds number in open channel flow? It is because open channel flow, it will flow because of gravity. So in Reynolds number, there are no function of gravity, but in Froude number we have gravity here to show that the gravity is influence the motion. So this is the reason why in open channel flow we always use the Froude number. And then what we know from the Froude number? From the Reynolds number, we know whether it is turbulent or laminar. But in Froude number, we could know about the subcritical, critical, or supercritical. So if the Froude number is less than 1, we call it as subcritical flow. Means that it is lower than the critical, subcritical. So if the Froude number is equal to 1, or when V is equal to square root GYH, so we call it as a critical flow. And then if the Froude number is larger than 1.0, so we call it as supercritical flow. So what is the subcritical, critical, and supercritical? It is actually the indicator to the hydraulic jump. As I said previously, in a dam construction and so on, so we afraid if every time we release the water, hydraulic jump will occur, because it will lead to catastrophic failure, a big failure there. So we must make sure that the energy of the water is not exceeding. So how to know that is by looking the Froude number. If the Froude number less than 1, we call it is subcritical, means it is not so critical, so we could relax with them. But if the Froude number is equal to 1, so it is the turning point. This is a critical point. Why it is critical? Because the water has a maximum energy to initiate hydraulic jump. And then if the Froude number is 1.0 is bigger than 1.0, so we call it a supercritical. Why? Because for sure the hydraulic jump will occur. Okay, so that's why we need to know about the Froude number, because as I said, in this topic, we are consider the hydraulic jump.